All right, you guys, it's time for rotation number 4. And this one is challenging, not gonna lie. There are parts to this homework that are gonna just take you a while. So I'm gonna hopscotch around and start with the easier ones, and then we'll work our way into the more difficult ones, and hopefully you'll have enough information to make your way through it. Okay, so actually I'm gonna skip number 1 for a little while just because that one is long and complicated. So let's go to number 2. So you're being asked to find the rotational kinetic energy of the two hands about the axis of rotation. All right, this has a few steps to it, but overall it's not that difficult. The main thing you want to ask yourself is, oh, sorry, I hit my my made-up tripod here. Is ask yourself, you know, you've got a minute hand and you've got an hour hand, and you got to figure out how fast are they going, each one of them. Okay, now they go around obviously in a circle, which is 2 pi radians, but you need to ask yourself, like, how long does it take for that to happen? Well, you know, the minute hand, let's face it, you know, like if it's here, it's going to come back around the following hour, right? So you know how long that takes. Oops, sorry, I'm off the page there. All right, it goes around in 60 minutes. The hour hand takes a bit longer. I mean, like, you have 4 p.m., well, when are you going to see it again? 4 a.m. So yeah, 2 pi radians, that's going to take 12 hours to get yourself there. So once you do some converting and get yourself into radians per second, you actually are most of the way there. All right, your kinetic energy, your rotational kinetic energy formula is 1/2 I omega squared. That would be for one hand, and then of course you've got the other hand. And you can look up, they tell you the shape, that way you can look up on page 278 the inertia formula, or you can look it up on Google. I suppose that would work too, that wonderful magical Google. Anyway, bottom line is this is not going to be a very large number, so don't be surprised if it's small. It is actually a small value. So that should give you a pretty good idea of how to take care of that one. Okay, let's move on. Okay. Number 3 may seem kind of confusing, at least when you first start, and I want to focus primarily on the diagram here. So I'm going to zoom in as best I can on this diagram. Okay, you're given the moment of inertia, good. You're given a value for I. You're told that the initial angular velocity is 0. And it rotates, and then there's the string, and then you have a tension. All right, and they give you that value of whatever. And it says the string does not slip. That's important. That tells you that it's turning. Okay, but it tells you that it gives you a distance for the string. Oops, sorry. Now I'm zoomed in so much you can't even see the word I'm about to write, which is string. Okay, so let's think. We want to know the angular speed of the top as it goes along. Ultimately, we want to know that. All right, so, well, let's think about this. We know the tension force. We know the force is being applied over a radius, and it's causing a torque, right? And you may be tempted to say, oh, well, I have a radius, it's that. No, it's not. No, it's not. That's the length of this, okay? The radius is actually for that part right there. I mean, obviously I kind of like just covered the whole thing up, but the idea, the force is being applied to this radius, the radius of the top of the top. And yeah, you don't know that. So good luck. You're not gonna be able to do that. All right, so what are my other options? If I can't use torque to figure out what's going on, what am I gonna do? Well, I'm so glad you asked. Okay, you do have quite a bit of information here. What you have to realize is that the force that's being applied over that distance, force and distance, right away, I'm hoping you're thinking work. I hope so. If you didn't, I thought of it for you. Okay, but when you have a force applied over a distance, it's telling me work. And what is the work doing? Work either makes something, gives it more energy or less. And what is happening in this case is the work is causing a change in the kinetic energy. It's going to actually go, of course, change is going to be final minus initial, right? And my initial is 0, so I can ignore that, right? So force times distance is going to be the kinetic energy final. What kind of a kinetic energy do I have? I only have rotational. So 1/2 I omega squared is going to be equal to my force times my distance. So that actually is a nice way to go about solving the problem. Now, since they've already given you the value of the inertia, that's actually incredibly helpful because you don't have to, try to figure out what the heck geometric shape that is. So luckily they gave you that. So hopefully that kind of gives you a workaround for that one. Now I'm going to just take a quick break here, but I'm going to keep the tape running because I don't want to try to splice this baby. Sorry about that, but I do hate sniffling on a video. It just seems rude. Okay, solid sphere released from height h, making an angle with the horizontal. I'm just going to draw a picture for this one. All right, so there's my height h. Here's some angle with the horizontal. Let's assume that we are going distance d down the hill. Okay, so calculate the speed of the sphere if it rolls without slipping. This is just like our Merrily We Roll Along lab. We have done this already, right? Where our potential energy is going to be equal to our kinetic energy rotational plus kinetic energy translational. Main thing here to keep in mind is the inertia of a sphere is 2/5 mr squared, and that omega r equals v. Because you are being asked for a linear velocity for your answer. So you want to get rid of the omega, and this is how you'll get rid of the omega, is by using this conversion factor. All right, and this will substitute in, and then off you go and you will solve. All right, for part B, calculate the speed if it reaches the bottom of the incline where it slides frictionlessly without rolling. Okay, so what we're seeing here is that you're skidding, okay? Again, just like the lab we just did, all of our potential energy is translational kinetic energy. And then comes part C, which seems a little bit dicey. What? What about time intervals? How the heck is that supposed to work? Okay, so let's look at what's going on here. All right, we are going to be basically traveling this distance per length of time. And, I have to be honest, I'm looking at how I have this solution done, and I don't necessarily like it very much because it's not accounting for the acceleration going down the incline. I'm pretty sure when I did this one, I was originally a little bit stuck, and I referred back to the textbook answers, and this is where I got it from. So I'm not 100% on this one, but here's the main thing. So avoiding the whole idea of, just bear with me here on this one, right? So here's my height, and of course theta and the distance. Okay, so if I am traveling down this inclined plane, what I am saying here is that, okay, sine of theta equals h over d. So d is going to be height divided by sine theta, right? Now, we are looking for, the relationship they're using here is vt equals delta x. But honestly, if I'm 100% honest here, that relationship doesn't hold as I accelerate down a hill. So I'm going to have to do a little more digging on this one, but bear with me for now. All right, what we're dealing with here, we want to know, of course, the time intervals. So there's my time. There's the part that I'm looking for. My d is my delta x. So if I want to know time, do I have room? I do. Okay, delta x divided by v will equal time, right? If my delta x is d, that's h on sine theta, divided by v, which is something I already figured out from the previous questions, that'll be my time. What'll end up happening when you're doing this, though, you have your velocities, of course, but this is going to be the same for each one, height over sine theta, so it's going to cancel out. So that's why I said just bear with me. Even though this relationship isn't perfect by any stretch, this part of it ends up canceling out. It ends up being a ratio of the velocities in any case. All right, so with that in mind, you can then solve for it. So the point is, you do this, you're going to substitute right here, which is where your velocity is. You're going to have, h on sine theta on v over h on sine theta on v. And the only different pieces will be the velocities. The h sine thetas are going to go away. So then make a ratio of your two velocities and solve, and you should have it. Okay, now let's work on the two that are more difficult. Number 5, the potter's wheel, is a little bit shorter than the one that than the first one. So I'm going to do the potter's wheel first, but I'm going to move this because I need a little bit of room. To write. Okay, so the potter's wheel. We are told that we're given this stone disc. I'm going to draw this one a little bit. All right, so you've got a stone disc. You're given the radius of the stone disc. And if it's a stone disc, let's face it, I can look up the formula for the inertia, right? So that's the important part. You're going to have some sort of formula here. You're told that it has an initial angular velocity of something, revs per minute. In my case, it says 50. And it says that the wheel stops, so you know that is 0. You know the time it takes to stop. My time is 6 seconds. And they press a wet rag against the rim and exert a radially inward force of 73 newtons. Okay, so the rag is going to be a force of friction, right? So let's face it, that's from the rag. The radially inward force that they're talking about is a normal force because you're crunching the atoms there, right? So mine is 73 newtons. So we have two forces. We have the force of the friction, which is actually perpendicular to the wheel, and you have a radially exerted inward force otherwise. And oh, look, we're being asked for mu. What? There's so many things, and now I gotta find mu? Well, the good news, of course, we know mu is force of friction divided by force normal. So we should be able to find that without too much difficulty. Okay, but where to begin? Well, the good news is we already know the bottom. Yay, we got one piece done. So the main thing is I gotta figure out the friction, right? I gotta figure out the friction. Now, what is the friction doing? The friction is causing a torque. The force of friction times the radius of the wheel is going to equal torque. Well, what else does torque equal? Torque also equals inertia times angular acceleration. That's our second definition for torque. So the bottom line is I can set those equal, right? Force of friction times the radius equals inertia times angular acceleration. Guess what? Let's see if I can get it all in one shot. I can. This stuff's going to let you figure out angular acceleration. This thing is going to let you, of course, figure out the inertia because it says inertia, right? The radius is already given to you. Then you can find the friction. Then you can find the coefficient of friction. So it's not quite as bad as it seems in the beginning. Like once you actually classify things and look around, it's not all that horrible. That is not necessarily the case for number 1. Number 1 is a little bit horrible. I like number 1. It's my kind of question. I really like doing Atwood machine questions. I have like this weird thing, I guess you would call it, but I don't really mind them. But they are long and they're complicated and they're a pain in the tuchus, and I appreciate that. So let's start. All right, you're given M1. You're given a wheel of mass M and radius R. And then there's this inclined plane, and you have mass 2. Okay, I'm going to put the inclined plane in there just to help us out. And we have theta. And let's see, they give you the value of M1. I'm just going to write mine down. I'm not going to do quite all of this, all right? But 1.7 kilograms for M1. They tell you the value for M2 minus 6.30 kilograms. And then you have a massless string. Luckily, something's massless, right? And then the radius of the big disc, I get one of 2.250. And then they give you the big M for the disc itself is 10. Okay, they move blah, blah, blah. They tell you theta. Oh my gosh, there's a lot of information in here. All right, and the coefficient of kinetic, oh great, so we've got friction too. All right, for both blocks. This is the one they're giving to me. All right, so what do we want to know? Oh, acceleration, nothing much. Nothing much. Okay, So in previous Atwood problems, what we have done is we have analyzed each of the blocks independently, made a system of equations, and solved. And we're going to do something similar to that. But the problem is now, what we did before, when we had a massless, frictionless pulley, is we figured that these tensions were identical. Well, thanks to this, they are no longer identical. So we are going to have to figure out tension number 2. I'm going to call it 2 because it's attached to mass 2. We're going to have to figure out tension number 1. And we're going to have to work with the pulley, which has inertia and angular acceleration all its own. Okay, so let's start with some free body diagrams, okay? And then what you want to do is you want to come up with stuff about each individual, like equations, translational equations for each of the 2 blocks, and then you need a torque equation for the pulley. All right, and then we're going to make a system out of that. So that ought to be fun. Okay, so let's just talk about block 1. Block 1, of course, has Fg, normal force. We don't really care too much about that, do we, though? Right, and we've got tension, well, we've got friction. We've got a friction going this way. And we're going to call this T1. Now, if I were going to write a translational relationship here, I would say, okay, the sum of the forces, always start with a, sorry, let me move this over. It's not 0. We are accelerating, okay? M1A equals, you probably want to do, F equals MA. That's always a good idea. All right, so M1A equals, what's the bigger force? Tension. What's the smaller force? Friction. And I hope you would see right away you're going to expand that out. Okay? Now, we can leave it like that for now, but I'll tell you, you're going to want to move things about so you get T1 by itself, because you're going to substitute that a little bit later. Okay? Now, how about my next one? Let's do my free body diagram. I've got Fg. And then I've got the little triangle guy, right? So I have M2G sine theta, M2G cosine theta, normal. Tension 2 is trying to go up. Let's see. We've got friction also trying to go up, trying to resist it, right? Because the overall motion's down the hill. So if I'm talking again, I would start with a basic premise here, but I'm not going to rewrite that. Let's do it again. M2A. Okay, what's this block? What's going to be bigger? The one going down the hill. What's going to be smaller? What's going up the hill? T2. And again, we want to substitute here. Now, you might be really tempted to say, well, I'll just move these around and solve for acceleration. No. You can't. You've got too many unknowns. You don't know T1, you don't know T2. You can't do that. They don't cancel. Dang it. All right, so now we got to talk about the pulley. All right, and again, I'm just going to warn you in advance, you're going to want to move that around. Okay? So that you get T2 isolated. Now let's talk about the pulley. For the pulley, the sum of the torques is not 0, right? Because it's rotating. What this means is that the torque is equal to angular moment of inertia, times angular acceleration. The torque is also equal to the force times the radius. These are the 2 biggies, all right? This is where your tensions are going to come in. Because what you want to remember, if I zoom in on the pulley, right, I have, here's tension 2, right, and it's being applied over that radius. And then here's tension 1, also being applied over that radius. Actually, I drew it in the wrong spot. It really should be like right there in the middle of the pulley, pulling on that radius. Otherwise, you think you have an angle and you're dealing with that, but you're not. Okay, so you've got all sorts of cuckoo for Cocoa Puffs things going on right there. We've got a couple tensions. So what we're going to do is say, well, the torque, the net torque, just like net force, is going to be equal to the bigger torque minus the smaller torque. And what's causing that? Well, the bigger torque is being caused by T2, and it's being applied over radius R. It should be capital R. What's my smaller one? It's T1, being applied over radius r. And what's that going to be equal to? That is going to be equal to the inertia times the angular acceleration. Now this may seem like the most unsolvable mess ever, but I'm here to tell you it's not. There's going to be a lot of lovely little cancelings, but there are going to be a lot of substitutions and a lot of little pieces you got to keep track of. Okay? You've got a formula for this. Find it. This, you're going to substitute. You're going to use this relationship because you want it to be in terms of linear acceleration. Okay? So substitute in there. The T2, I told you about that one. That's going to come from your translational equation that you did up above. And the same thing goes for this one. So substitute that in as well. Now that sounds like we'll take 4 pages to write it down, but I'm going to guarantee you a bunch of stuff is going to drop out and you're going to be able to find your acceleration in the end. Okay, so just remember, you're looking for linear acceleration. Granted, you're going to have some acceleration in your relationship over here. You're going to have some acceleration in your relationship over here. So be careful with your negatives. Do your algebra, slowly and carefully. But it's not impossible to solve. It's actually kind of easy once you get everything substituted in. Once you do all that math, you're going to get an actual number for this problem when it comes to acceleration. And then the second part of the question says, find tension 1 and tension 2. Well, of course, once you've got the linear acceleration, you can go back to these and you can find it. It's not that hard. It's just going to take you a little bit of time. Okay, so work carefully and see me if you absolutely can't solve it, and we'll take a look. All right, guys, there you go, homework number 4. Have fun.